Hello everyone, welcome back to the lecture series on Foundations of Deep Learning, Concepts and Applications. In our previous lecture, we have discussed about the different algorithms for object detection like RCNN framework, fast and faster RCNN. In today's session, we will look into a very widely used object detection model, which is you look only once. We call it as Yolo, and we will see at the Yolo V1 architecture and working. V1 means the first version or the original version of the Yolo model. So, we will start with Yolo V1. You only look once. Yolo proposes an end-to-end neural network that makes predictions of bounding boxes and class probabilities all at once. Okay. So, it is an end-to-end network where it predicts the bounding boxes as well as the class probabilities all simultaneously. It is introduced by Joseph Redmond et al. In 2015 in the paper You Only Look Once Unified Real-Time Object Detection. So, this is the reference paper. I urge all of you to look into it. Now, we will see how Yolo V1 works. Suppose you have an input image, okay, like this, and then these are the different steps through which Yolo proceeds. So, we will see one by one what are they. So, this is your input image, okay, and then the first step is going here. So, we see the image is divided into S cross S grids. So, there is a grid which is placed over the image, and each grid cell is responsible for detecting objects whose centers fall inside the cell. So, each grid is detecting some object, is responsible for detecting some object that is present inside the grid. Okay. Now, if you see, I have highlighted the portion with the dog. Now, if you see even only with the dog, there are so many grids that are inside the dog's highlighted part. So, what happens is once we try to find out what are the grids that are present or which are the grids which are having the dog's image, then we try to find out the bounding boxes which is shown here. So, each grid cell output the bounding boxes, position and size and a confidence score. Confidence score is what? It is the confidence that the object is present inside the box, okay, with what confidence you are telling that one. So, this box gives you bounding boxes plus confidence. Now, we look at this part which is the class probability map. If we look at this part or the image, you see the dog portion is having the pixels or the grids here are having blue color. There is a cycle, the cycle portion is having yellow, and then there is a car at the back background. So, that portion is pink and the other portion is red. So, here whatever the pixels or the grids which are having that blue color, that belongs to dog class, and yellow colored grids belong to the cycle class. So, what happens is this basically gives you a class probability map. It maps what are the classes that are present inside the image. Then after the class probability map is done, then this bounding boxes plus confidence score and the class probability map, they join together to find out the final detection. So, in this final detection we see there is the dog is in blue bounding box, the cycle is there in yellow bounding box, the car is there in the pink bounding box. Okay. So, this is the entire framework in which Yolo V1 works. Now, we will slowly look into each and every step more in details. So, I have kept the image here just for reference. Now, we will look into this portion, bounding box plus confidence. So, I have taken this portion image here, and the question may arise, Why so many rectangles are there? We have the grids. This is a clear picture with the grids. But when we are putting the bounding boxes, there are a lot of bounding boxes, overlapping bounding boxes. Where are they coming from? So, the answer is each grid cell predicts multiple bounding boxes. So, from each grid cell there will be multiple bounding boxes. Some will be exactly correct, some may be little offset left side, some may be little offset right side, some may be up, some may be down. Each predicted box has position xy, which is the center relative to the grid cell, and the size, which is the width and the height relative to the whole image. Okay. So, since each grid cell predicts multiple bounding boxes, so there are so many overlapping boxes here. Also, this predicts the confidence score. What is the confidence score? How do we calculate the confidence score? Confidence score, as I was telling, that it is the confidence with which we can, or the model can tell that there is an object inside the box or not. So, it is calculated as probability of an object existing into the IOU score, which is the union over intersection over union between the truth and the predicted one. Okay. So, probability that an object exists into the IOU score. Okay. So, that is how the confidence score is calculated. Now again, so we have done, now again I have kept this image here for reference. Now we will look into the class probability map, how it is calculated. So, this class probability map, as I was telling, that different classes are having different colored grids associated. Each grid predicts conditional class probability. What is the conditional class probability? That is probability of class I given there is an object. Given there is an object inside the grid, what is the probability that object is class I? For example, I will just write probability of dog class given an object exists in that grid. Okay. So, that is how the conditional class probability is computed. Now, during test time what happens? One set of class probabilities per grid cell is computed regardless of the number of bounding boxes. So, we have seen there are multiple number of bounding boxes that are coming from each grid. But regardless of the number of bounding boxes that are coming from each grid, only one set of class probability per grid cell will be calculated, and like this. So, from here suppose this grid have multiple bounding boxes, but the set that will come from here is say dog 0.9, bicycle 0.06, car 0.04. So, these are the class probabilities. Okay. And how do we calculate it? So, probability of class I given the object into probability that there is an object into the IOU score between the truth or the ground truth and the predicted, which is equal to probability of class I into IOU between truth and the predicted. So, this is the formula that is used for class probability calculations. Now, this is or the conditional class probability calculation. Now, this is basically the highlighted part is your confidence score for the bounding box. This gives the confidence that there is an object present, and the remaining part tells given there is an object present which is taken care by this part, what is the probability that it belongs to class I. Okay. Class specific confidence scores are given for each box. So, for each box class specific confidence scores are given. Okay. Then we come into the final detection part. So, we have seen image divided grid, bounding box plus confidence score, class probability map, and then how these two are merged together to get the final detections. So, in the final detection, if we see there is a bounding box, blue colored bounding blocks around the dog, then there is a yellow colored bounding box around the cycle and pink colored bounding box around the car. Now, what happens here is, there are a lot of bounding boxes here. What we have done is, we have done a non-max suppression. An object can have multiple boxes with IOU beyond the threshold, okay, that is possible. Now, Keeping all those boxes might include noise. We do not want multiple boxes to come for one particular object inside the image. Non-max suppression, as we have seen in our previous lecture also, it suppresses the duplicate ones and gives only the exactly fitting bounding box. So, non-max suppression to keep only the boxes with the highest probability of detection scores. Okay. And this non-max suppression is used during the inference time. So, with the use of non-max suppression, what we are getting? We are getting one single box per object. Now, we will have a look into the architecture of Yolo V1 model. So, the architecture looks like this. There are various convolution layers, and if we calculate them, it has 24 convolution layers followed by 2 fully connected layers. So, these are the fully connected layers, and 24 why? Because from here one convolution layer, one convolution here, 1, 2, 3, 4, from here 4 are coming. Here it is 1 and 2, this entire block is multiplied into 4, that means there are 8 plus another 2 convolution layer, that is equal to 10. From here how many coming? These 2 convolution layers into 2, 2 into 2 is 4 plus another 2, that is equal to 6. Then from here it is another 2. So, how many it is? 1 plus 1 2 plus 4 6 plus 10 16 plus 6 22 plus 2, which is your 24. So, there are 24 convolution layers followed by 2 fully connected layers. Initial convolution layers of the network extract features from the image. We all know initial layers of convolution, they are meant specifically designed to get the features extracted from the image, and fully connected layers predict the output probabilities and the coordinates. Okay. Now, Yolo V1 treats detection as a regression problem, and Yolo V1 for each grid cell it predicts bounding box coordinates x, y, w and h, confidence score C. This is confidence score is confidence whether it will be an object or no object, confidence score that the object is present inside the box, and then the class probability for the object is belonging to class I. Okay. Now, when we are training the Yolo V model, we have to see into the loss functions, because loss functions will be back propagated and then we will get the output predictions much more accurate. So, we will have a quick look into what does the loss function of Yolo V1 look like. So, it is a big expression, it may be looking very complex, but actually it is very simple. We will look into all the terms one by one. So, these first 2 terms, okay, first 2, this one as well as this one as well as this entire thing, they are localization loss, that means the loss that is coming from the position and size. Okay. Then the other one, next one, this block, it is coming from confidence loss, object versus no object. So, this entire thing is confidence loss. And the third one is, what is it? It is the classification loss per class. What is the loss? Whether if it is not correct, whether if the model is not predicting the class properly, we get a loss from here. Okay. Now, we will one by one we will look into what are these symbols or what are these terms. So, this lambda coordinate, this penalizes incorrect prediction of x and y, and usually the default value chosen is 5. Okay. And if we see, there is a summation from 0 I equal to 0 to s square, y s square, because there are s cross s number of grids, and there is a summation j equal to 0 to b, b is the number of bounding boxes per grid. Okay. xi is the ground truth x coordinate for the bounding box, xi hat is the predicted one, similarly yi and yi hat. So, this is coming from localization loss, which is basically the position xy coordinates. So, this is related to position. What about the next term? So, okay, before going there to the next term, I missed this one. So, this term 1 ij object, this term is 1 only for the box responsible for detecting the object. If there is an object, then only this will be 1, otherwise it becomes a 0. So, for the background boxes where there is no object, this term becomes 0. So, we are not bothered about the loss that is coming from there. But if there is an object there for which this term becomes 1, then we will calculate the loss from that bounding box. Then coming to the next one, this lambda coordinate, it penalizes bad prediction of box sizes. What is there inside? It is having the width and height terms here. Width, this Wi is basically your ground truth, and this Wi hat is your predicted one, and this is your ground truth height, and this is your predicted height. Okay. So, this gives me the loss for bad box sizes. Size should be exactly matching, where it should not be too big or too small, so that it does not have the entire object inside the box, neither it should be too big. So, this is related to the size of the box. Okay. Then, okay. Now, here there is another term. What is this one? This is a part of the confidence loss, that means object versus no object. What exactly it means? It will tell if there is an object and the model tells there is no object, then the loss will come into picture here. So, for this one, the ground truth confidence is 1. Why? That means the ground truth is telling that there is an object inside, and this term is 1 we have seen only for the boxes where we have an object, and this is our predicted confidence. Based on it, the loss will be calculated. Okay. Now, look at this term, the second term also. There is one object, ij object, and here it is 1 ij for no object. What does it mean? That means this term is 1 only for the boxes without the object. So, wherever there is no object, for those only it will calculate, and here the lambda no object default value is 0.5. This is kept because a lot of boxes may come from the background. So, background is the place where there will be no objects that are present, and then Ci and Ci hat are the ground truth and the predicted confidence. So, in this case your Ci will be ground truth confidence, which will be equal to 0, which means there is no object that is inside the box. Okay. And the last term, which is the classification loss per class specific loss, and it penalizes incorrect class probability predictions. It penalizes the incorrect class predictions. Okay. So, this is the ground truth and this is the predicted class or the predictions for the class. Okay. Now, there may be a question that comes that for all these losses, we have taken xi minus xi hat square plus yi minus yi hat square. Everywhere we have just taken the actual minus the predicted one, then squared it. Only in the case of this position size of the box where height and width are there we have taken square root terms. Why we have done that one? Let us have a look. Why width and height terms are not having square root in the loss term? For that one, let us take an example. Suppose the true width is 200 and the predicted width is 190. In that case, if I do true width W true minus W predicted square, what do I get? It is 200 minus 190 square, which is equal to 10 square, that is 100. Okay. Now, think of the case, suppose the true width is 20 and the predicted width is 10. In that case also Wt minus Wp square equal to 20 minus 10 whole square, that is also 10 square, which is equal to 100. But if we see here, this is a very small error. So, it is around 5% error, whereas it is 50% error, 5% error here and this is 50% error, but say both are giving same loss. If we take the square root like this, W of Wt minus square root of Wp whole square, what do I get? 200 minus square root of 190 square, that is equal to how much it is? 14.14 minus 13.78, which is equal to 0.36, sorry, 0.36. If we do the same calculation here, that is square root of 0.36 square actually, okay. So, whatever it comes. Now, here it is what it is 20 square root of 20 minus square root of 10 whole square, that is nothing but 4.47 minus 1.77 square, so which is 2.7 square. Now, we can see here the error is more compared to here. So, Yolo wants relative error to matter more than the absolute error. That is the reason that square root terms are taken in the size when the width and the height are coming into picture. Okay. Now, variants of Yolo. So, we studied Yolo V1, which is the first or the original version of Yolo framework. It came in 2016, Yolo V1. Then 2017 Yolo V2 came, then V3 2018, 2020 V4 and V5 came, 2021 Yolo R and Yolo X came into people discovered, or they came into Yolo X and Yolo R came into picture. 2022 Yolo V6 and V7 were introduced, 23 Yolo V8 and Yolo NAS, and 2024 we have Yolo V9, V10 and V11, 25 there is the version V12, and it keeps going with a better performance as we go on. The higher the versions, performance improves. Now, this is a picture depicting how the object detection looks like in a Yolo framework. So, it detects the objects with some score, which is the confidence score, and this is how it looks like. Okay. So, with this one I come to the end of this session. Let us quickly summarize what we have seen. So, this Yolo is a model, object detection model, which is heavily used for object detection tasks, very heavily used. So, we have seen the architecture, which consists of 24 convolution layers and 2 fully connected layers, and then we have seen the working where each image is divided into grids, and then from the grids we have the bounding boxes with some confidence score, and then there is a class probability map, and then both of them are joined together or combined together to give the final predictions. So, these are the things we have seen, and how the calculations happen for the class probability map, and how the the confidence scores are calculated in terms of the intersection over union statistics. Those things we have seen, and then we have seen what are the what is the loss that is associated with the Yolo V1, the original this one. So, the losses come from 3 different three different places. One is for the localization, that is the box's size and shape, and then there will be the confidence whether there is an object or not object, and then the class probability. And we have looked into what are each and every term there which is coming into the loss calculation. So, with this one I conclude today's session. I hope you got an understanding about the YOLO V working in V1, YOLO V1's working and the architecture. In the next session, you will have hands-on session in object detection algorithms, and there will be YOLO V also will be done in the hands-on session. Till that time, enjoy learning. Thank you all.